Now let's have another look at a projectile problem. Give you a chance to have another go at it. Let's first by just looking at a ball being kicked. It's going to go up and over like that, right? Now, there's only one force. We'll draw the ball in various positions. Only one force acting on that ball, and that's gravity. And F weight force equals mg is the gravitational weight force. So at all points, I could draw the force like that, right? From our equation F equals ma, we know that force and acceleration are always in the same direction. So this is also, this is also the direction of the acceleration the whole way through. The fact that it slows down as it goes up and speeds up as it comes down, the acceleration is never changing. What is changing is the velocity. Now the thing about the velocity, if we have a velocity at the start of 20 meters per second like this, 20 meters per second, we'll put it on an angle of 30 degrees, then we can break that up into two components. That's why we look at vectors. If we've got a horizontal component and a vertical component, those two add up to make that vector 20 meters per second. And we're going to have to work out those components. And the reason we're going to have to work out those components is because the horizontal component of velocity, we call it VH, is not affected by the gravitational force, because the gravitational force is down and the horizontal velocity is across. Not even a teeny weeny component of the gravitational weight force is acting to oppose this horizontal velocity, sorry. So that horizontal velocity is going to stay constant. What's going to change is this vertical force, this vertical velocity, and that's because it's got a force acting vertical, and that force is gravity. So that velocity, it starts off quite high. This is its value when the ball gets kicked. I'm just talking the vertical component. It slowly gets less and less as the ball travels up until at the top it's 0. Then it turns around and starts to get bigger and bigger as the ball comes down, right? Those red ones are the velocities. Remember what I said about acceleration? Constant throughout the whole thing, right? It's only the vertical velocity that's changing. If we draw the horizontal velocity, I said that was constant the whole time, because it doesn't get acted on by a force. So in projectile, we absolutely have to break everything up into the two components, and that's why the vectors are so important. So having done that, let's work out our forces. V horizontal and V vertical equals, this is using the angle, 20 times the horizontal is going to be cos of 30 degrees. The vertical is the opposite side, so it's 20 times sine of 30 degrees. Sine of 30 degrees is 0.5, remember we talked about that, so I can tell immediately that it's going to be 20 meters per second. That's the vertical velocity, 10 meters per second. And this other one's going to be about 16 or 17, the horizontal. So let's just do that on our calculator. 20 times cos of 30 is 17.3 meters per second. So now we've broken it into our components, we can start to calculate things. What do we want to calculate? Well, we want to calculate the height it goes to. We want to calculate the range. Also, to get the height, once we get the height, we can get the time it takes to get up to that height. So that's the next thing to do. So how are we going to calculate the height? This is where we've got to look at our kinematics formulas. And the one I would jump to using first up is Vf squared is equal to Vi squared plus 2AD. The reason I go with that is because if we go back to our projectile, at its maximum height, its vertical velocity is 0. When we're calculating this stage, we're just looking at the vertical velocity. Remember, that's the one that's changing. And it goes from maximum down at the bottom to 0 at the top. So we want to know how high it's going to go. Now in this formula here, if I know that Vf at the top is 0, 0 squared equals Vi squared plus 2AD. Vi, we know, is the vertical velocity on takeoff, which is 10 squared. We know gravity, 2 times 9.8 times distance. Now, the thing here is that the gravity is negative. We've got a little negative in there. So that would make this whole thing negative, wouldn't it? So we can say that 0 squared equals 10 squared plus minus 2 times 9.8, which is 19.6 d. Right? Now if we add 19.6 d to both sides, we would get 19.6 d equals 10 squared, which is equal to 100. We divide both sides by 19.6. Then we're going to get d is equal to, because these 19.6's cancel, it's going to be equal to 100 divided by 19.6. And we get 5.1. So now we know how high that ball goes. It goes, and it goes up 5.1 meters. Sounds pretty normal for a reasonable kick of a soccer ball, doesn't it? Now, I want to know the time it takes to get up to that maximum point. And the way I can do that is by grabbing another one of my kinematics formulas. I'll just get another page. Another one of my kinematics formulas to get the time. And what I'm looking for here is a formula that will do that. Vf equals Vi plus At. You're just going to have to ignore that noise. V final equals V initial plus At. How's that going to help us? Well, we already said that Vf at the top was equal to 0, right? And Vi, we know, is equal to 10, plus At, which is equal to 9.8 t. But as we said before, we get a problem with a negative. Right? Now that negative means that we are saying 10 minus 9.8 t is equal to 0. So we can solve this. Add 9.8 t to both sides. Equals 10. So divide both sides by 9.8. We've got t equals 10 divided by 9.8, which is equal to 1.02.
Sorry, John, do you have any beakers?
So 1.02 is the time. But remember, this is the time just to get to the top. Right? That was the time to get to the top, because that's when Vf equals 0. So based on that, we know that that's 1.02. That's 1.02. So the total time of flight is twice that. 2.04 seconds. Now we've got the total time of flight. Let's close this door. We can work out the range. Now the range is going to be easy because we've got a constant velocity. The constant velocity, or VH, remember from our calculation, was equal to 17.3 meters per second. Now if we've got a velocity of 17.3 meters per second, which is not changing, and it goes at that speed for 2.04 seconds, it becomes a real easy thing to calculate the distance it travels. We just use our old formula, which was V equals D over T, right? So D equals VT, V being 17.3 and T being 2.04. Equals 35.3. So what we've been able to calculate is, sorry about it's meant to be a symmetrical parabola, but what we've been able to calculate is the height of 5.1 meters, the range of 35.3 meters. We've been able to calculate the time it takes to get up, 1.02 seconds, 1.02, 1.02. So we've calculated everything. One thing that I would point out to you with this is the velocity it takes off at, and remember velocity is not just direction but the magnitude, it will be like that when it lands. So it will be the same magnitude, the same angle to the ground. Alright, so what formulas did we use to do that problem? We used this one. We used that formula to calculate the height that it went to. We used this kinematics formula to calculate the time. And we use this formula to calculate the range. So you definitely need to know your formulas, and you definitely need to remember to split up. The velocity we're using here is the horizontal one for the range. When we're calculating the height, we're just using the vertical velocity. So you definitely have to split these velocities, or the projectile velocity, up into its horizontal and vertical components. Again, when we're working out the time, we're just using the vertical velocity. So the time of flight for any projectile just depends on the vertical velocity.